Okay. So I gave you guys this sheet with the handouts that are or the packet with conversions and abbreviations. So this is, you guys should have this separately, but also posted in here. And I wanted to talk a little bit about this because it seems that we got a little confused of how to use the conversion chart. So we know that, there we go. So in this chart, basically, they're giving you the conversions for example, here we have 1 teaspoon equals 5 mLs. So it basically means that the 1 teaspoon is going to equal 5 mLs. But in order to use it for our advantages, we need to turn it into a ratio. So I'm going to do the algebraic way right now so I can show you guys how we do that. That's kind of, there we go, erase that. So we're going to go ahead and do that. So we're going to say 1 teaspoon, which is 1 TSP, is going to equal to 5 mLs, right? Now, how can I make that a ratio without changing what this statement is saying? Because this is just basically one statement saying 1 teaspoon equals 5 mLs. So if we multiply the equation by 1, am I changing anything in there? No, right? So I'm just going to go ahead and move my teaspoon to the other side. 1 teaspoon, that will cancel by dividing. And I'm just going to have 1 teaspoon equals 1. Is this statement incorrect? Because 1 teaspoon is 5 mLs, right? 5 mLs divided by 5 mLs is 1. And 5 mLs is 1 teaspoon. And 1 teaspoon divided by 1 teaspoon is 1, right? So therefore, I can get a ratio by just setting it equal to 1 and then moving the other unit to the other side. And I can do that to both sides. I can say 1 teaspoon equals 5 mLs times 1, and then divide the 5 mLs in the other side. These two will cancel, and that statement is still correct because 5 mLs equals 1 teaspoon, and therefore that's still going to equal to 1. So that's the way that you're supposed to be using your ratios most of the time, or your conversion chart. Most of the time, we're just going to be ignoring the equal to 1, and we're going to be using our ratio or our fraction in here. So 1 teaspoon over 5 or 5 over 1 teaspoon, depending on what you're trying to find or how you want to set up your problem. So let's take for another example, or let's say I want to find how many ounces are in 4 pints. Okay, so I'm going for pints, 2 ounces. So in order to do this, we need to know which one's bigger and which one's smaller. Pints usually are this bigger size, and ounces are going to be the smaller size. So whenever you go from big to small, most of the time we're going to be multiplying. Oh, actually, we're going to multiply. When we're going from small to big, we're dividing. But I'm going to go ahead and use my ratios here that I have in order to go to ounces. And I'm going to use dimension analysis in order to keep it a little bit clean. So we talk about dimension analysis, which is just basically this format that we have. And we're going to go from pints. We got 4 pints. And then our end value is going to be ounces, right? Or that's what we're looking for. So there's no conversion from pints to ounces, but there is a conversion from pints to mLs, right? So what's my pints to mLs? 473 mLs. So remember that we said whenever we're going from big to small, we're multiplying. So we're going to put that on the top, 473 mLs, because that'll be 4 pints times 473. And then the bottom, we're going to have 1 pint. What that creates too is that this 2 will cancel. The pints will cancel. And now we cannot go straight into ounces. So we have to draw another section to it. So we have this. So now do we have a conversion that changes mLs to ounces? Our mLs to ounces will be 1 ounce equals how many mLs? 30, right? So our mLs are going to be in the bottom because we want to cancel the units. And also mLs going to ounces, it's going to, ounces are a bigger unit, right? 1 mL equals 30 ounces. Backwards, 1 ounce equals 30 mLs. So 1 ounce equals 30 mLs. So therefore, we're going to go ahead and divide that, and we're going to put the 1 ounce on top. So the mLs will cancel, and then we just have to multiply everything across and then divide at the end. So that'll be 4 divided times 73. That'll be 4 times 473 equals 1,892. 1,892. And 1 times 30, 30. So at the end, I just have to divide this section. 1,882 divided by 30. Divided by 30, which is going to equal to 63 point. If I want to run to the tens, how high is that going to go? 1. Okay, so that'll be 0.1 ounces, right? Because ounces was what we're trying to get, and ounces is the last unit that we're getting in there. So that's how we use the conversion table. And again, it kind of got me work because I did tell you guys have you could put the table in there, the conversion tables in your note card. So if you had this in your note card and you did not know how to use it, that's what I'm looking for, to see if you guys know how to use the conversion table and how to utilize it to your advantage. So that's just that example that I put in there. So I'll give you again the definition of why we use conversion, measurement of conversions. So basically the whole world uses it. The main problem is here in the United States, because here we usually use our units of food, feet, inches, we use pounds, but the rest of the world uses kilograms, meters, they use grams and all this other things. So most of these drugs that are coming from overseas, they come in those measurements. So therefore we need to know our units of conversions, or our standard units of conversions, to change them from their units into our units that we use in here for better usage, and in order to calculate things. One of the basic rules you guys want to go ahead and try to remember is this one that I highlighted, and then I also bolded and did underline underneath so you guys can see it, is this 2 rules right here. If you need to convert from a large unit to a small unit, you're going to be multiplying. If you're going to be converting from a smaller unit to a large unit, you're going to be dividing. Okay, so that's basically the standard rule. But in order to use that rule, you need to know which units are smaller compared to which unit to the other units. For example, if we're talking about liters and mLs, which one's going to be bigger? The liter, right? So if we're talking about grams and micrograms, grams is going to be the bigger, micrograms is going to be the smallest ones. So you need to know, you need to compare each single unit to see which one's going to be bigger and small. Okay, so dimension analysis, they also has another name that goes by, which is the train track method, because it looks like a train track right here. So we have our conversion factors, and I give you the conversion factors for length. We don't really use length a lot, except whenever we're going to be talking about pediatric, and for whenever we're talking about the height of a patient. So that's going to come in effect more later towards the semester, but you guys need to know that 1 foot equals 12 inches. You don't really need to know the yards to feet, but we're going to do some examples in here, and the mile to 5,280 feet. You don't have to know them for this class, but it'll be nice to know them in the future in case you want to do some higher education, that it'd be easier to just memorize all the stuff. So the train track method, or dimension analysis, how we call it here, basically is the same setup that we're doing, or that we did earlier. So for example, if I have, let me see, Sean, how tall are you? 6 feet. I'm just going to say you're 6 foot to make it easy. So if you have someone that's 6 feet, how many inches is that? 72 inches. When we can go 12 inches equals what? 1 foot. Our feet will cancel. Why did I pick the lighter colors? Our feet will cancel. And 6 times 12 equals 72. And then 1 times, 1 is going to be 1, which is going to be 72 divided by 1 is 72. So, and what we left off is inches. So usually the train track method or dimension analysis tends to be the one that allows students to pick, because it's a lot easier to manage, and you just can plug in everything in there. But that only works if you know your conversions. if you don't know your conversions and how to set them up, then that is where the problem lies. One of the biggest mistakes that I saw in the test that almost everyone got was this. So let me erase this. I was asking how many kilograms is in 5 pounds. So my conversion for kilograms is 1 kilogram equals what? 2.2 pounds, right? So using the train track method, where would I put my 2.2 pounds? At the bottom or in the top? Or in other words, am I going from small to big or big to small? Small to big, right? So I'm dividing because 1 kilogram is 2.2 pounds. This one's going to be, well, this one's equal, but this unit is going to be a little bit bigger. So we're going to go ahead and divide because we're going from small to big to kilogram. So it's going to be 2.2 and then 1 kilogram. So if I divide it by 2.2, is it right? By 2.2, 2.3 kilograms. Okay. I think it's said to the tens or to the ones, hundreds, but we're just going to keep at 2.3 kilograms. The pounds will cancel. And then the only thing that you left is with kilograms. The major mistake that I saw is that the students that missed this, they went and did this. You're multiplying pounds by pounds. So if you multiply pounds by pounds, you're gonna get 11. You're gonna get 11. I think 5 times 10. Yeah, it's gonna be 11 something. But the mistake was that you get 11 kilograms. That's the one that most people got. But you are dividing because you're trying to find out how many kilograms there is. Okay. So you can set up your train track like this by asking yourself, how can I cancel these pounds? Okay, so the way to cancel those pounds is to put pounds in the bottom and my other one on top. Okay, because as you move to the right, you're gonna be canceling your units because they're dividing. So that's why you cancel that and you cancel that. If you did not cancel your units or the units that you have at the beginning to the end, then you're not gonna have the correct answer. Okay, so that's probably gonna be the hardest part whenever we're setting up this problem with the train track method, is saying how we're gonna be setting these problems up. So the other way that we can do it is through ratio proportion. So ratio proportion is just doing it through the butterfly method, right? So that's a little bit different than this. And our ratio proportion is just gonna be 1 kilogram is 2.2 pounds equals, and then I have 5 pounds. Why did I put my pounds in the bottom? Same unit and the other unit is in the denominator, right? So we're gonna keep it the same. So whenever we cross multiply and then divide, it's gonna be 2.4 kilograms. Okay, so if you do ratio proportion, you gotta have the same units in the same spot. If you do dimension analysis, you gotta make sure you cancel those units out in order to get to the units that you want. So those are the 2 different forms. And your book shows you the different ways to it. So here I have an example for you guys, and we're gonna go from inches to centimeters, was it, or miles? So they give us this amount of inches, which is gonna be 126,720 inches. And we're gonna go ahead and turn that into miles. See that they have the inches here, and they're gonna cancel them by putting it in the bottom. So that will cancel basically the inches out. Then you left over with 1 foot, because 1 foot is 12 inches, which canceled the feet with the next conversion, which is 1 mile equals 5,280 feet. And then you're just gonna go ahead and multiply across and then divide at the end by the 2 numbers that you have at the end. So which are this on the bottom. For ratio proportion, the way that you would have been doing it, you have to do 2 of them, because how many conversions are we using? 2, right? We're using the 1 foot is 12 inches and 1 mile equals 5,280 feet. So that'll be 720 over X equals, and that's inches, equals 12 inches over 1. And then once you get your answer, you're going to put the other one pretty much the same way. And you're going to be doing 2 different conversions like that. This one's a little bit longer. This one will be a lot easier to use. Okay. Whenever you're dealing with multiple conversions that you're going to be having. So you need to know how many steps you're going to be needing, because the more steps you require, the longer these train tracks are going to get. Okay. The less steps is going to be the less amount of space you're going to be needing. Any questions about this? We okay with dimension analysis? Okay, that's okay. We'll get to practice more in a little bit. So here's an example problem. So you know your sister loves milkshakes. She uses 8 quarts of milk to make a milkshake. How many gallons is she using? We're converting from a smaller unit, quarts, to a larger unit, gallons. So we divide, right? So we're going to divide. But which conversion factor am I going to be using? The 1 gallon to quarts, the 1 pint to 2 cups, or the 1 quart to 4 cups? Gallon to quarts, because we need what? She is using quarts, and we're going to gallons, and we already have a conversion. So I'm going to do the train track method right now. I think it's just 1 step. So it's 8 quarts. And what's my conversion? 1 gallon to 4 quarts. So where am I going to put my 4 quarts? Bottom. And the 1 gallon on top, right? See, he said that we're dividing. So 8 times 1, 8, right? And there's nothing here, so I just cross this over. Do my quarts cancel out? Quarts, quarts. And what am I left over? Gallons. So 8 divided by 4? 2 gallons. Okay. That's using the train track method. This one is probably the easier one to use, but you do have to know both of them, because as we move forward, especially right now with liquid, we're going to be doing a lot of ratio proportion, because it's one of the things that we use to get real quick math. Or whenever we get our doses, whenever we're trying to find for a single dose. So remember, whenever you're going from big to small, you're always going to be dividing. When you're going from small to big, no, backwards. Whenever you go from big to small, you're multiplying. Whenever you go from small to big, you're dividing. Basically, your rules that we mentioned back here. So these ones are going to be your key factors. So try to memorize that stuff and try to understand your ratio proportion, your table, in order to know how to use it properly. So here's some measuring units, and I just give you more examples of why we need conversions. So for us, since we're doing here, since we're here in pharmacy, and we're not really going to be doing physics or measuring all this other stuff, thank God, because that would be really hard. We're just going to be using our milligrams. So we don't use the centimeters, even though this is for lengths, but we don't use any of this stuff except for kilograms and milligrams. Our pounds are going to be really important. Why do we need to know our pounds to ounces when we're talking about babies? Yes. Oh. Yes. But when we don't measure the babies by pounds, right? A baby does not weigh, most babies don't weigh a pound, right? So we usually tell them it's like, it's this many ounces, or this baby weighs this many ounces. So we need to know the, yes.
So you say ounces, but like why? Like my son's and I feel like 2 weeks ago when she was like, oh, he's 29 inches. And I was like, 29 inches.
That's the yeah, that's the length. But we do measure them by length, and later on we're gonna find out why we need to know our length and our mass in ounces, because there is a charge that we use, and you guys are gonna be doing. Later on you guys are gonna need rulers, by the way. A ruler to measure the how much of the doses they're gonna require based on the height or the length and the ounces that the baby weighs. That's gonna be towards our pediatric baby or neonatal mathematics that we're gonna do. But we need to know that conversion, the pound to ounces, and then the inches to centimeters to get to that. But yeah, they measure them because that's how they base the drugs. That's how they're going to find the body surface area of the baby. So this one's very important, and this one's very important. 1.2 inches. For our milligrams, we need to know our kilograms, grams, milligrams, and micrograms. Okay. And there's another one that I guess the question that went from kilograms to micrograms. Remember, there's a kilogram, there's a gram, there's a milligram, and there's a microgram. Some of the students skip the milligram and went straight from gram to microgram. So for each step, you gotta be dividing 1,000. So you divide 1,000 to go to grams, 1,000 to go to milligrams, and 1,000 to go to micrograms. So I remember there's 4 of them. Okay. So these are some of the questions that I had in the test, and these are some of the common lengths measurements or metric systems that we're going to be using for our length. We have the 10 millimeters, 1 centimeter, 1,000 millimeters, 1 meter, 1,000 centimeters equals 1 meter, and 1,000 meters equals 1 kilogram or kilometer. Weight, we have 1,000 nanograms, 1 microgram, 1,000 micrograms, 1 milligram, and 1,000 milligrams to 1 gram, and 1,000 grams to 1 kilogram. Most of the time you see them flip. This is from your book, so they put them like this, but they're the same thing. So we have 1,000, 1 ml equals 1 cc. So you're gonna see that more probably want to start moving to your oral solutions in your labs. And also once you get to the IB lab, you're gonna see cc's, and that's gonna confuse some of the students because what is a cc? Cc just stands for cubic centimeter, okay? A cubic centimeter is just a little cube that has been cut into 4, and it's just like that. 1 ml fits in a cubic centimeter in there, okay? So therefore, 1 ml equals 1 cc. So whenever you see cc's, it's just a 1 ml. Why does that keep popping up? Okay. So your book uses this method, which is just multiplication and then divide at the end. But isn't this method pretty much the same thing as the train track methods? Okay. So the only thing that they change is they put the multiply sign, but the train track method is pretty much the same thing that they're using here. So we're gonna go ahead and work some of these problems that we had in the test. So 3/4 of a liter. And I think probably because I didn't bring a visual, it's gonna be our last time this happened, but this is a liter, okay? So this is a liter. This is a half a liter. Don't worry about what it says right here. Because it's 500 ml, okay? So this is 1,000 ml, this is 500 ml, so half a liter. And this is 1/4 of a liter because it's 250 ml, okay? So 1 liter, 3/4, how much is it gonna be? How many mLs? If 1/4 is 250, 3/4 is 750, yes. So another way you could have come up with that answer, where's my pen? It's like this. You have a liter is 1,000 mLs, and you want to know how many quarters is 1/4. So 1,000 divided by 4 equals 250. And how many quarters you have? 3. So multiply times 3 equals 750. Okay, so that would have been 750 mLs. So you could have gone just and said 750 mLs. What's my conversion to go from teaspoons to mLs? 1 teaspoon is how many mLs? 5 mLs, right? Where am I going to put my 5 mLs, on top or bottom? Bottom. 5 mLs and my teaspoons. Is that going to cancel my mLs? Yes. And what am I going to be left over? And I'm looking for teaspoons. So that'd be 750 divided by 5 equals what? 150 teaspoons. Okay. So for the next one, we have 1 pound to 5 pounds to kilograms. We already worked that one, and we said it was 2.3, I think, kilograms. Grams to micrograms. So we have 11 grams. How many conversions am I going to do? 2, right? Because I have milligrams and then I have micrograms. So 1 milligram equals how many grams? Well, how many grams is 1 milligram? That's better one. So 1 gram 1,000 milligrams. Where am I going to put my grams? At the bottom, grams, and at the top. But I'm going from big to small, right? So I'm going, so I'm multiplying, right? Yeah. So big to small, multiply. Small to big, divide. So yeah, so that we're going to multiply that by 1,000. But I need micrograms. So what's my conversion to 1 milligram equals how many micrograms? 1,000 too, right? Where are we going to put our micrograms? On the top, because we're still multiplying, because we're going from milligrams to micrograms, and milligrams is the bigger unit than micrograms. And the other one's going to go in the bottom, which is milligrams. Now we're going to cancel. Our grams will cancel, grams will cancel, milligrams will cancel, milligrams will cancel, and the only thing that we left is micrograms. So that's 11 times 1,000 times 1,000. How much is that? 11 million, right? Now, is this the same thing? If I just say, oh, well, I'm just multiplying 2,000 here. Is 11 times 2,000 the same? No, right? Because 11 by 2,000 will be what? 22,000? Yeah, it would be like 22,000, but that's not the same as this. So you got to do it step by step, multiply one at a time. You cannot just go ahead and say, oh, it's 2,000 here, so I'm going to multiply by 2,000. That's not correct. That's not the correct way to do it. So this will be your correct setup. The next one, we have 2.2 pounds equals how many grams? Where can I find how many grams is 1 pound? Or can we find that out? Yes. So there you go. So we know 1 kilogram. We go back to my question. 1 kilogram equals 2.2 pounds. And 1 kilogram is how many grams? 1,000 grams. Therefore, I have 2.2 pounds. I gotta make them first into a kilogram. Where do I put my 2.2 pounds in the bottom, right? 2 pounds and then 1 kilogram. And where do I put my gram stuff in here? On top, right? Grams and 1 kilogram. Cancel the units to check if you did it properly. So you have divided, cancel. That cancels with this. And then the 2.2 divided by 2.2, 1, right? So what's left? 1,000 grams. Okay. Okay. So whenever. Okay. Yeah. Let's say we're just going. Erase. There we go. Let's say we're just going to kilograms. What happens when I do 2.2 divided by 2.2? 1, right? So what you're doing whenever you're moving across, you're going to divide at the end. So it doesn't really matter if I just multiply all the way across and then divide by that number. If I see that I can cancel the same numbers in like these little spots like this. So whenever we're canceling, we're just making it 1. Because whenever we multiply by 1, do we change anything? No, right? It stays the same. So that's just 1, and that's just 1. And then what I have left over was 1,000 grams over 1 kilogram. Okay. And that's just 1 times 1,000 and 1 times 1 kilogram. Okay, there we go. And then the next one, we have 10 teaspoons equals how many mLs? What's my conversion factor for teaspoons to mLs? 1 teaspoon equals 5 mLs. Okay, so we have 10 teaspoons. Where am I going to put my teaspoons portion? Top or bottom?
teaspoons.
Yeah. Yes. Okay, and then do I have any other steps to do go? No, right? So that's just the only one. Cancel my teaspoons. 10 times 5. Okay, so we have 50 mLs. So whenever we have, again, whenever we have multiple steps, we want to be using dimension analysis if you know your conversion factors and if you know how to set it properly. If you're more comfortable doing proportion, ratio proportion, then you can do that too. But that might take a little bit more space and more time to do it for this. So we're just going to go ahead. I'm going to give you a couple minutes to practice this. I'll give you the conversions right here. So let's see. So we have kilograms, how many pounds to kilograms? So you know 1 kilogram equals 2.2 pounds. How many drinks a quart? So how many gallons does she drink? So quarts, you know 1 gallon equals 4 quarts. And divided by 5 pounds are how many ounces? So 1 pound equals 16 ounces. So go ahead and do those 3. The kilogram to pounds might not be exactly what you see in the choices, but that's because they use a more accurate type of conversion, but it should be somewhere close to it. For which one? No, they use the pounds to ounces. So we have pounds to ounces. Remember, 1 pound equals 16 ounces. So 1 pound equals 26 ounces.
She's saying that in our lab, when we do,
Oh, the ounces to milligrams?
yeah, when we're doing
Yeah.
solid, it should be 20.
Yeah, that's the yeah, but that's the ounces to milligrams. If you guys use that in the lab, we'll probably be using that too here. Yeah. So I'm just gonna set it up. After the special proportion. Okay, what's the answer for number 1? 154. So that's 70 divided 70 times 2.2, 154. So it's like this one. And again, they use a more accurate one. They use 2.2 something, 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 something. So that's why they got the extra stuff in there. And then 1 quart equals how many gallons? 1 gallon. And then how many ounces is this? 80, right? Because 5 times 16 is gonna be 80. And again, 2 different ways you can solve them, either through dimension analysis or through ratio proportion. Whichever you choose is gonna be up to you. So this is just a little more problems from your book. So a medical patient needs to receive, a neonatal patient needs to receive a medication based on their weight in grams. The patient weighs 4 ounces and 6 ounces. How many grams does the baby weigh? So this is what we call a multi-step problem. Why is it multi-step problem? Because they give us pounds, ounces, and we need to find out at the end grams. So we have 3 different steps that we need to do, because we could find how many kilograms everything is, but that might be the harder way to go about it. The best way to go about it would be first to change your pounds to ounces. So I have 1 pound equals what? Pound equals 16 ounces. And how many pounds do I have? 4 pounds X. Okay. So that'd be 16 times 4. How much is that? Equals 64. X equals 64 ounces. And how many ounces did I have to begin with? Plus 6. So how many total ounces is that? 70 ounces. Now, what's my other conversion about ounces to milligrams? 1 ounce equals how many milligrams? And we're going to use the one that you guys used upstairs. So that's 28.35. So we have 28.35 milligrams. So I have a total of 70 ounces. Yes.
It says so we'll need to go back and convert
Oh,
milligrams to grams.
yeah.
But we don't have it, how many grams are
And then now,
in ounce.
Wait.
Like 0.3.
yeah, we just go with the gram, sorry, skip the step, ounces. So we're gonna go ahead, well, we want grams. So 1 ounce is 28.35 grams. Oh, not milligrams. So that's what I'm seeing. Okay, sorry. Yeah, okay. That's grams. Okay. So since we're going at ounces, so we need to cancel our ounces, and we have 28.35 grams equals what? How many grams is that? So that'll be 70 times 28.35. 1084.5 grams. So see how it was a multi-step problem where we have to go from our pounds to ounces, and then from our ounces to our grams. And then we just added this. So this is type of problems that you're going to be seeing more in pediatrics. And again, because we're going to be doing everything in ounces and or grams whenever we're weighing the baby, or whenever we're talking about the different rules that they're going to be applying to them. So the next one, Richard weighs 220 pounds. How much does he weigh in kilograms? That's an easy one, right? So we have 220 pounds. 1 kilogram equals what? And are we dividing the 2.2 or multiplying? Dividing 2.2 pounds is 1 kilogram. So that'll be, should be 10, right? 20 divided by 2.2. See it myself in my head. There we go. 100 kilograms. So a physician writes 133 micrograms levothyroxine in the mouse date, and once a day, the levothyroxine tablets in the shelves are equal to in milligrams. How many milligrams will each tablet need to be? So we're just trying to convert the micrograms to milligrams. So are we going big to small or small to big? Small to big. So that means that we're going to have to divide, right? So 137 micrograms. What's my conversion factor from 1 milligram to how many micrograms? 1,000 micrograms. So my my milligrams at the bottom. No, backwards. Where's my? I'm trying to cancel my micrograms. So that'll be 1,000 micrograms equals 1 milligram. And see that we're dividing. So that should be 0.137 micrograms. because my micrograms will cancel with micrograms. Another question for the test. You guys remember this one? Yes. So a lot of you guys got the first part. Second part was kind of funky. Okay, so we have doctor prescribes the patient Tegretol 600 milligrams, PO Q4. Dispense 180 tablets. What is on the hand? It's Tegretol 200 milligrams. What is my frequency here? For Q4, which is 6 doses, right? 6 doses. My dose is what? 600 milligrams, right? No, my dose is 600 milligrams. The form of it is a tablet, okay? So it's a tablet. So how many tablets the patient needs to take for one dose? 3, right? 3 tablets, because each tablet is what? 200 tablets. So how many days supply, or how many days the tablet would last? How many days is gonna last if we dispense 180? 10 days, right? But how do we find that out? So that's where I lost some of you guys. Because remember that in order to find your amount of days, you need to multiply one dose, which is 3 tablets, times the amount of doses they're taking a day, right? Which is 6 doses. And then divide by the amount that you have, right? I think this is the formula that Ms. Liz gave you upstairs. But I just show you step by step. So. Oh, backwards. It's backwards. So. Yeah, I just saw it. It's backwards, but the answer should be 10. So that would be the 180. 180 divided by 18 equals 10. The answer was going to be 10. So the order to give the patient 45 milligrams of codeine, you have 30 milligrams core tablets. How many tablets should you dispense for a now dose? And then I tell you in the bottom, what does this mean? Remember, you are dispensing it from a retail pharmacy. Okay, so the dose is 45 milligrams and we have 35. So how many tablets is that? One tablet is 30 milligrams. And what we need is 45 milligrams is over X. Or you can do 45 milligrams with dimension analysis, 30 milligrams, 1 tablet, which equals 1.5, right? Either one is 1.5. X equals 1.5. 1 to 5, no, 1.5. For this one? Yeah, well, that's what I'm saying. Like, that's where I was gonna go next. I was like, you rushing. No, but like I said, if we're saying that this is gonna be dispensed in the retail pharmacy, remember, in retail pharmacy, we cannot send 1.5 tablets, right? Mostly because of insurance purposes, but also because that's how we're training and everything. So how many times we're gonna send in total? 2 tablets, okay? That other half is the patient is gonna waste it the way that you're probably not gonna waste it. It's morphine, but they're supposed to waste it in the proper way. Oh, that kind of covers the review section of conversions, dimension analysis, division proportion. Are you guys a little bit better with that now? We're okay now with that stuff? Because it's gonna get a little bit more complicated now that we're adding solutions, now that we're gonna be adding liquids into the mix. So we're gonna go ahead and do, we've been dealing with solids ourselves and not all solids. We've been dealing mostly with tablets, capsules, but they're pretty much about the same except the ointments, because the ointments are gonna measure a different way depending on the ointment itself. But tablets, suppositories, capsules, and all the different forms of tablets, you calculate it the same way. Liquids are a little bit different because you're gonna have to find what we call concentration. So before we get to that, even start talking about that, I want to go through some of the vocabulary that you guys are going to be seeing, just in case you might have forgotten or probably never seen it before. So we're going to do a little bit of chemistry. Don't worry, we're not going to calculate any chemical compounds. We're just going to go through the vocabulary. So in here, I'm giving you the 4 states of matter, which is the solid, liquid, gas, and then plasma. most of the time, we're not going to be dealing with gas and the plasma. We are mostly going to be dealing with solid and liquid. We do have some aerosols, but they're mostly liquid form. Some of them are powders, depending on what they're giving. As far for gas, there are some gases that pharmacies sometimes deal with, but that's more on the hospital side for surgeries, whenever they're giving, I guess, a laughing gas or whenever they're trying to knock out someone. So just know that there are different forms of states of matter. So a solid can come in different forms too. Like we say, it comes in capsules and everything. For our powder or our liquids that we're gonna have to dissolve, then most of the time are gonna come in solid or a powdery form or what we call crystals. So you're gonna see them. Oh, this is why I brought this. So you're gonna see them in this state. So you got, there's a powder in here. Most of us refer that to powder. Sometimes you're gonna see like little crystals, like those geo crystals you sometimes see in the arcades. But the same thing, they're just going to be our powder volume or powder that's contained in the bottle that we have to dilute. When we dilute it, we're just going to go ahead and make it into a liquid. But when it goes into a liquid, sometimes it goes through a gas phase too, because of the chemical reactions in here. And therefore, sometimes the volume will be less than when you add it. Sometimes it will be more. And when I mean the volume, I mean the liquid volume, right? So that's what we're measuring. We're not going to be measuring the gas itself. So dissolving liquids. So we're going to be dissolving liquids, and that should be liquids and ash powders, because sometimes we're going to be doing what we call double dilution, especially when we deal with pediatrics. We're going to be grabbing the concentration from the vial or the amount of mL we need, and we're going to add more liquid into it in order to lower the concentration of it. So whenever we do that, we just go ahead and start adding liquid to it, and it has to mix homogeneously, what we call, which means the same throughout. So there cannot be a separation to it, especially when we're talking about IVs, because whenever it's IVs or whenever it's heterogeneous, then that means that you can see the separation of it. And I'll give you the definitions of them in a minute. But you're going to have two parts. One that's going to be the solvent, one's going to be the solute. All of them are going to come together to make a solution. So when we're talking about solution, we're talking about the mixture of both. So in here, we have the solute right now inside the powder. That's what we consider the solute. The solvent is going to be the liquid or the still water and then so whatever that we're going to be adding into it. And once it's mixed together and everything's clear, it's going to be a solution. So it goes through 3 different steps. Well, it goes through 1, but you know the different parts to it. Now, whenever we're talking about concentration, we're talking about the amount of units of drug there is per ml, okay? So sometimes it's going to be the milligrams because we measure milligrams, sometimes micrograms, sometimes milliequivalents, millimoles, units, and so on, so on. The list goes on. That depends on the drug that you have and the concentration that it gives you. Now, concentration can vary from step to step. So in here in the bottom, I gave you a little example of a water that was that they put some coloring to it. Notice that it goes from one side is the less concentrated water that they have to the more concentrated there is. And you see the more of the coloring they put in there, the darker it gets. That's pretty much about the same idea with the drugs, but we're working backwards because we are adding so we are adding a solvent into our mixes, or we are adding a solvent into our solvents in here. So the less liquid we get, the more concentrated it's going to be. Okay, the more liquid we put in here, the more the less concentrated the less liquid we put, the more concentrated. The more liquid, the less concentrated. So that's how it's going to be working for our drugs. So we go to that. So what is a homogeneous mixture? So I mentioned homogeneous, and that basically means a mixture that's going to be the same throughout. That is not going. You're not going to see a separation. For example, if you mix oil and water, if you let it sit out in the desk or anything like that, you see that the water and the oil will separate, right? That's what we call. I mean, so that's not a homogeneous mixture. But whenever you add salt to water, you know that the salt dissolves into the water and you cannot see the salt afterwards, right? So that's a homogeneous mixture. That means that it is the same throughout. So that's basically the meaning of it. And most of the time we just call it a solution. because it's just going to be clear, or it's going to be a certain color, but it's going to be the same throughout the whole thing. Now, a heterogeneous mixture is going to be a mixture that you can see the separation of it. Most of the time, these are going to be our suspensions. They're going to be our tinctures sometimes, and there might be some of the other liquids that don't mix correctly with the powder or with the other liquids. Now, those usually are not for IB use. They're mostly for oral use, or sometimes for the ear. But most of the time, we're going to call them suspensions ourselves. So for homogeneous, you're going to hear them as solutions. For heterogeneous, you're going to hear them as suspensions. Okay. And you might see some of the stuff up there with Miss Liz and probably the hospital lab. Once you reach it, they're going to refer to them as elixirs. Elixirs basically contain some alcohol into it, and they are a homogeneous mixture, so they're not going to be separated. But the other one is going to be suspensions. So a suspension, I got to tell you guys right now. So suspension is basically something that we're going to have to shake vigorously, because we want it to be as together, or as we don't want the drug to be settled at the bottom, because if we try to draw anything like that, we're just going to be drawing out the liquid on top and not the actual drug. So whenever we have a suspension, we got to shake, and we always got to put a shake sticker on top of it, because if not, they're not going to give the actual drug to it, or they might give higher concentrations of the drug. So that's just one of the important things as suspensions. Solutions, you don't really have to mix them, they stay mixed throughout, but it's just good to be shaking all the liquids, unless it doesn't supposed to be shaken. So before we go there, I want you guys to remind you about the rights of medication administration. So we, most of the time, I think you guys heard about 5 rights, probably from Spain, if you got through 1301 with her, or for Mr. Dunn. So we have the 5 rights here, or the 8 rights. So we need to make sure that we have the right person, the right medication, the right dose, the right time, the right route, the right documentation. The patient has the right to refuse and the right to respond to it, okay? But the main ones that we deal with, or the ones that we're going to focus on ourselves, is going to be our medication, our dose, our time, and our route. Most of the times, and we focus that ourselves because that's where we're going to be doing a lot of the calculations ourselves. With the type of medication we do, whether it be a tablet, capsule, an ointment, suppository, or a suspension or a solution, we're just going to go ahead and have the right medication. With that right medication, it's going to give us the right strength of it, and it's going to give us the right concentration. The dose, as you can see from the previous example, doses can vary from the frequency that they have. So if a frequency is Q8, how many doses is that? 3 doses. And if it's Q6, 4 doses, okay? So those are gonna be our doses, and our times, also when the medication is gonna be given, and that again goes with the frequencies that we have. For example, if something's Q12, it's gonna be 2 doses. If it needs to be given every day at 9 a.m. or at 2100, which is the military time, that's gonna be once a day. And the route. So our route of administration basically goes tied in whenever we're in the lab and in here, tied into our medication, and to see if it makes sense. So if if we go to the shelf and we grab a ointment medication or an IV, Levobutral, I think there's one that's IV, but the route of administration is orally, then we know that it's not the right medication, because the oral version is going to be little ampoules that are plastic. Okay, and those are going to go through the mouth because they're going to breathe it in. So you guys need to know the right route. So that's why I ask you guys to learn those abbreviations about the routes and everything. So it's just a little statement about the right stuff that we need to look at for our patients and for ourselves in order to do proper calculation. So this is from your book, section 2, about calculating our solution. And your book gives you a 5-step method, which is pretty much something that we've been doing, asking ourselves this question. So you gotta ask yourself the question, you gotta see your data, you gotta see which formula you're gonna be using or which method, and then do the math and see if it works. So that's the 5-step 5 steps that the book uses for that. See that they use here in our, oh, this is not 1, 2, there we go. See that we have, There we go. That should be the one.
Chapter.
Chapter 9, I think it was basic medication calculations. Yeah, this is the basic medication calculation. We started with the first section, which is the tablets and capsules. Now we're going to the next section, which is the oral solutions. So we have in here that they did the ratio, the dimension analysis. So just remember, this is dimension analysis. They just put it in like that, and then we're going to multiply it like through and divide at the end. This is the ratio proportion they use, but we can just go ahead and work it out together so we can see, because I know your book tends to be a little bit confusing. So let me erase this. So most of the time, whenever we're dealing with solutions, we're gonna have to transfer or measure stuff in a syringe or stuff that measures liquids like beakers and or our oral syringes that we have in there. So we're gonna be needing a couple things in order to do this calculation. One of the things is gonna be our concentration. So in here we have an example, 50 milligrams of a drug is received and 10 ml vial, and they have a concentration right here. So our concentration is always gonna be a formal measurement over ml. So what measurement is that gonna be most of the time, except for ml. So it's gonna be like milligrams, equivalents, grams, anything. It can be any other form of measurement like that, but always has to be over mLs, okay? So you have your concentration here. You have your size of the vial here, a 10 ml, that size of the vial. And then you have your dose here. So that's my data that my problem gave me. So I have my dose, size of bottle, and my concentration. And with that, I can pretty much find any problem that they give me. So how many mLs should be withdrawn from the vial? If my dose is 50 milligrams, so I'm gonna write it down here. That's my dose, 50 milligrams. And my concentration is 100 milligrams per ml, which is just 100 milligrams per 1 ml. Or in the, I guess this other format. Are those two the same thing? 100 milligrams equals 1 ml? Or 100 milligrams divided by ml. Remember that we can just put a 1 in front of draw. Where's my mouse? There. In here, we're multiplying by 1. So if we divide 1 ml and 1 ml, 1 ml equals 100 milligrams. And 100 milligrams is 1 ml. So therefore, it's going to equal to 1. But you just want your concentration, and you got to know that you can move your concentration around. You can either put it like that, 100 milligrams to 1 ml, or you can say 1 ml is 100 milligrams. Okay, so you can put it back and forth depending on what type of calculation you're trying to do. Okay, so for right now, which one am I going to be needing in order to plug it into my train tracks here? This one, right? Because I need to divide by 100 milligrams in order to cancel the 50 milligrams. 1 ml. So how many mLs is that? 0.5 mLs, which is the same thing that you both got. So we need to draw 0.5 mLs from our vial, or from the vial, in order to get to our dose. How many mLs do I have left over once I drew that? If that's the size of the vial. 9.5. So we have 9.5, and we just subtract the amount of mLs. So if I say that I want to find out how many doses I can get out from 10 mLs, if my dose is 0.5 mLs, how many doses is that? How can we figure that out? So let me erase this. So let me write a ratio. So 1 dose equals how many mLs? 0.5 mLs, right? That's my ratio. I want to know how many doses there is in 10 mLs. What can I do to cancel the 10 mLs using this ratio? Where should I put the 0.5 mLs? Yes, in the bottom. And 1 dose on top. So the mLs will cancel, and the only thing that's left over is my dose. So 10 divided by 0.5. Should be 5 mLs, right? I think. Oh, 5 doses, not mLs, 5 doses. Ah. There we go. 5 doses. Everyone got to 5 doses? 20 doses. Oh, yeah. 10 divided by 0.5. You're not doing math today. I apologize. That'll be 20 doses. So that'll be 20 doses in there. Doses. So see how I just came out with the ratio using the data that I have? Just using the data that I have, that 1 dose equals 0.5 mLs, I can use that to find out how many doses I have in the entire bottle. You're gonna have questions like that. Sometimes that's gonna be important because whenever you're trying to save for wastage, you need to find out how many doses can you take out from 1 vial. Because if this is a bottle that we can only use once inside the beehood, then you want to make sure that you take as many doses from it, because if you only take 0.5 mLs from it, you'll be wasting 9.5 mLs, right? So you don't want to be using something like that because that'll be a big waste. Or you want to take as many doses as you can. So we're going over reading the drug label ourselves, and we got done some examples of how to read the drug label. And pretty much all the labels are going to have the same thing. They're going to have your full volume. They're going to have your strength. They're going to give you a concentration. Now, they might give you concentrations in different forms of measurements. So see, they have a concentration there in milliequivalents, and they have a concentration there in milligrams. Okay, so depending on the problem that they might ask you, they might ask you to solve for milliequivalents. They might give you to ask you how many mLs are in 20 milliequivalents. So therefore, you're going to use the milliequivalent part. If they ask you to use milligrams, they're going to ask you how many mLs are in certain amount of milligrams. Okay, so that's why they give you different forms of it. Some of them just will give you one, depending on how the doctor is going to be measuring this stuff. And then it has all the other common stuff like your NDC, your manufacturer, and so on. And then it gives you more information here. How many ratios do you guys see here? So let me go back to my ratios. So we have one ratio here, right? 40 milligrams over 1 ml. We have another ratio here, 0.3225 milliequivalents per milligram over 1 ml. We have my ratio of 2 grams over 50 mLs, and that's my size of the bottle and the strength of it. And then it gives a ratio here too. Each 50 mLs contains 2 grams, and then so it doesn't give you the 1 per ml. But see, 1, 2, 3 different ratios, and I can use those ratios to solve the different problems they might give you. Either any of them. How can we make this into percentage? I already have my ratio of 2 grams equals is 50 mLs. So percentage, what do we do? Remember, percent is over what? 100. And then I can just go ahead, find X, which is going to be 4, right? And 4 over 100 is what percent? 4%. Okay. So there's 4% of that drug in there. Don't forget how to change to percentages, because you guys are going to see that also in math too. Okay, so we're going to work some problems now that we got some of the basics down. So we have, this is straight from your chapter book. So this is easy problem to start with. So we have 20 milligrams is ordered, and what's available is 50 milligrams of mLs. So we're going to set up, we're going to do some with ratio proportions, some with train tracks. Okay, so we can practice both of them. So what's my dose? 20 milligrams. I'll start with what I need, which is 20 milligrams. My concentration is 50 milligrams per ml. So that is equal to 50 milligrams equals 1 ml. So how many, where do I put my milligrams? The bottom or the top? The bottom, right? I'm trying to cancel my milligrams. So that'll be 1 ml. So the milligrams will cancel, and that's 20 divided by 50. equals 0.4 mLs. Okay. So I'm going to turn it off. You guys can see that on your paper, right? So I'm going to turn it off, work on that, and I'll show you the answers in a minute. Okay, you guys ready? Okay. Do your answers match up to mine?
Would we change that CC to ML just because CC?
Yeah, you could. It's the same thing. Sorry, I should have done that. But yeah, you're right. Yes, once you see it's just 1 ml. So. Everyone's okay with that? Yes. Okay. Now, like I was mentioning before, sometimes your drugs are going to be measuring in different forms of measurements. Okay. In here, they measure the drugs based on the amount of units they have per the substance in the ml. So units are going to be one another form of measurement you're going to see in your bios or in your drugs. Most of the drugs that use this are going to be insulins because they use the 100 units per 1 ml. You're going to be seeing that in some of the expensive medications because they want to measure the units, the amount of units it has in there per ml or per certain amount of mLs. That doesn't change our process of calculating this stuff. Okay, the same thing. If they're going to give you units, so they're going to give you a dose in units. Your concentration should be in units too. So let's say this was milligrams, and that was milligrams. Is that going to change the amount of or the way that we do our calculations? No, right? It's still the same thing. So this is going to be, so just because it says unit, we just have to match it up with the right concentration that is units. Now, again, just like in your bag that I show you, they might give you units and they might give you milligrams in the other side. So you're gonna go ahead and pick the units or the units parts that you're gonna be using. So for this one, we have 6,000 units for a dose. Units over 5,000 units because we want to cancel the units. And always write units out. Don't just do U. Because if I give you 7, is that 75 units or is that 750? You cannot tell, right? So you always write the word units out. Don't just write the U. And that's for so to avoid errors. And 1 cc equals 1 ml. So that'll be 6,000 divided by 5,000, which is going to equal 1.2 mLs because my units will cancel. And then I just have 1.2 mLs. Next one, my dose is 300,000 units. And for those that know how to cancel the zeros, you can go ahead and cancel the zeros at the beginning. But if you don't know how to do that, don't do it. It's gonna confuse you. Units. So we just go ahead and write everything down. 200,000 units over 1 ml. So that'll be 300 divided by 2,000 divided by 200,000. I mean, which is 1.5 mLs. Okay. Do you guys see a pattern that how are we doing this now? As you guys practice it, what is the pattern that we're doing? We're grabbing our those.
I was like, you put your those on this side.
Yeah.
And
And then you put the.
you use on the side and you put the top.
So what's the end process that we're doing, or what are we doing? Dividing, right? So we're dividing our doses over our concentration. So we only have to go to our calculator and go ahead and do, that's 500,000, right? 500,000 divided by 1 million. And that's going to give us our answer. That only works when it's over 1 ml, okay? So that's why it's important to reduce it to the 1 ml mark, or to know how to reduce our fractions to 1 ml. Because once it's 1 ml, we can just go ahead and straight plug it into our calculator, and that will give us our answer right away, instead of doing this whole process. So again, we're just gonna go ahead, since it's to the 1 ml, and just do 500 divided by 1 million, and that's gonna give us 0.5. Or you can go ahead and do this whole process too. But again, I'm just showing you shortcuts in order to kill some time, in order to move faster. Whichever way you decide to do it, that'll be up to you. Also, you guys can do ratio proportion with it. So we're gonna go ahead and stop here. We only have 2 more slides, which is just goes over the powder. So we're gonna pick up here next time, and we're gonna go more in detail about powder. We're gonna learn about powder volumes, our dilute volume, and our final volume. And we're gonna go over the temperature ranges. I know you guys been having that paper for temperature ranges or temperature for a while now, but this is the reason we're gonna start talking about it, because some of the powders will be needed to be refrigerated. And we need to find out which ones are those and where do we put them, okay? If you guys don't have any questions, you guys are free to go. Yeah. Hold on, let me stop this recording.